Hello, everybody, and welcome to Day 2 of Honors Global Climate Change. Today, we're going to look at the structure of the atmosphere. The atmosphere is where a lot of our climate happens, and therefore, if we want to understand our climate and how it's changing, we need to understand what's going on in the air around us. So come on along, and we'll take a look at our atmosphere together. So today, we're taking a look at our atmosphere, and before we get into that, I just want to give you a couple words from Dr. Jane Goodall. You cannot get through a single day without having an impact on the world around you. What you do makes a difference, and you have to decide what kind of difference you want to make. Today, you are going to be able to explain the layers of the atmosphere and how these impact our lives. Alrighty. So, we are going to be doing a demo in a few minutes over here, but this demo does take a while to get ready, and so I just want to start the lights on it, and then while those lights are going, we're going to be heating up the water in these graduated cylinders, and we'll be back to talk about this demo in a little bit after we watch a little video.
In the empty blackness of space, surrounded by hostile planets and freezing vacuum, planet Earth is an oasis of life. And all because of our protective cocoon of gas. This blanket of air shapes everything we see on Earth. It protects, insulates, and sustains us. It carries water around the globe and shields us from cosmic impacts and killer radiation. It's time to uncover the invisible wonder that is our atmosphere. Down here on the Earth, we rarely give much thought to our atmosphere. Because we can't see, smell, taste, or hear it, we take it for granted. But our air is all that stands between us and the vacuum of space.
We've got this canopy that provides us a lot more than just an atmosphere to breathe in. It definitely shields us.
The atmosphere is divided into 5 distinctive layers: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each layer is less dense than the one below, stretching miles above our heads.
How far out it goes, depending on which scientist you talk to. Some say it ends at 300 miles, some say it extends out to Mars.
We live in the layer closest to the ground. Here in the troposphere, the air is thickest and the pressure greatest. Our bodies are perfectly matched to these conditions.
Our chemistry, our very nature, our metabolism is completely shaped by the atmosphere.
To appreciate our atmosphere, we'll rise through its layers, traveling from the planet's surface, miles up above the mountains and the clouds, to the very edge of space. August 16th, 1960. One man is preparing for a record-breaking journey into the mysterious skies above. To a lethal world above 99% of the Earth's air, where an unprotected human would die in seconds, where the temperatures plunge to 67 below, and the air pressure is 1/100th of that at the surface. Colonel Joseph Kittinger will travel almost 20 miles high, and then he will jump. This is a key military mission, one of the first steps in the space race. Kittinger will be testing the human body's resistance to high altitude, low pressure, and rapid free fall. He will be trialing new technology he hopes will protect him.
It had never been done before, but we were not there to set a record. We were there to gather information that we needed for our space program and for our high-flying aviators.
Ground crew prepares his vehicle, a helium balloon, and a rudimentary open-sided gondola.
Just an open gondola. It was designed just to carry me up. It was a space platform, an elevator, I called it.
At 5:30, Kittinger's preparations are over. He boards the gondola.
My crew chief said, are you ready? And I said, I'm ready, let's go. It was a very smooth takeoff, and I started ascending. Up, up, up.
30 minutes after takeoff, Kittinger reaches 29,000 feet, the middle of the troposphere. At this altitude, the air is so thin that each breath contains only a third of the oxygen found at sea level. Kittinger breathes from gas bottles connected to his sealed helmet. He's still barely a third of the way to the jump point. There are another 14 miles to go, and the air pressure is dropping rapidly.
So at about 40,000 feet, suddenly the pressure suit starts inflating, and that's when you start checking it to make certain that it's working properly.
But there is a crucial fault in the suit. The glove covering his right hand is not sealed.
I had an option to tell the ground that I had the problem, and I knew that if I did, they'd probably make me abort the flight. And I was concerned that if we had to abort that flight, that we would have been turned down to try to do it again. So I didn't tell them.
Kittinger prays that this is an isolated fault and continues to climb at 1,000 feet per minute. After 89 minutes, he approaches his target altitude. The balloon's climb slows and then stalls. Kittinger is in the mid-stratosphere, a record 102,800 feet high. At this altitude, he is 3 times higher than the tallest mountain. Despite the pain from his bloated right hand, Kittinger can still glimpse the wonder around him.
I was not there as a poet. I was not there as a philosopher. I was there as an engineer. But it was very beautiful. All of a sudden, looking up, the sky is no longer blue. The sky is black. It was a phenomenal perch, standing on the doorsteps of space, looking out.
No man has been here before. Without his protective gear, Kittinger would be dead in seconds. And it is now time to make the long, swift journey down.
When it came time for me to jump, I was ready to jump because I was heading back toward a more friendly environment, a friendly planet that we're used to. I'd made this jump 1,000 times in my mind. I'd gone through every step 1,000 times. Well, just before I jumped, I said a silent prayer. I reached over and hit a button that started the cameras going. And then I just did a little hop off the step of the gondola. You can't tell that you're going fast. You can't tell anything. And I looked up at the balloon, and the balloon was firing into space. And I said, gosh, that's amazing. And then I realized it was me that was going down at a fantastic rate, and the balloon was standing still.
He falls for 16 miles. The thin air offers almost no resistance. He reaches 614 miles an hour, approaching the speed of sound. After a record-breaking 4 minutes and 36 seconds of freefall, Kittinger opens the main parachute. He drifts down to the desert floor and lands.
We were just elated because we had accomplished what we set out to do. There was a lot of people who said we couldn't do it, and we proved that we could do it.
The mission has been a stunning success. Kittinger's skydiving record stands to this day. He takes his first deep breath of air with a newfound appreciation for our atmosphere.
It was a relief to be back on the planet Earth that we love so much. A planet that has an atmosphere that we can live daily.
Kittinger forged a dizzying path through the atmosphere. Our journey begins just a few feet off the ground with the air we breathe. We take for granted Earth's blend of gases, the perfect mix for heat and energy. And astronomer David Grinspoon believes we'd be hard-pressed to find its equal anywhere.
The more we learn about planets, the more we learn that they're all individuals. They're like people in that sense. So as far as what we know now, Earth's atmosphere is completely unique.
In the past century, telescopes and space probes have uncovered the extreme atmospheres of our neighboring planets. A journey across our solar system reveals exactly how unusual Earth is. Clouds of near-frozen gas flow over the icy surfaces of Uranus and Neptune, while the sun has blasted away the atmospheres of Mars and Mercury.
To me, it seems as though Mercury doesn't have an atmosphere at all. But in fact, if you were on the surface of Mercury, it would look to you as if you were out in outer space.
In contrast, Jupiter and Saturn are all atmosphere.
Unlike Earth, Jupiter doesn't really have a solid surface that you could stand on and then have your head up in the atmosphere looking at the clouds. It's just a giant gas ball.
Only one other planet shares the Earth's thick atmosphere and rocky surface. Our near neighbor, Venus. But even here, there are striking differences. Dr. David Crisp has spent 20 years studying Venus's acrid air.
Imagine you're at the surface of the planet Venus. You're at pressures that are high enough to crush a nuclear submarine. The pressures there are about 90 times the pressure of the Earth's surface.
This pressure is combined with extreme heat, 900 degrees Fahrenheit, hot enough to melt lead. Clouds drift over the baked surface, but they are not water vapor. Venus's clouds are made of concentrated sulfuric acid. Venus is a stark example of how extreme an atmosphere can be. But the real mystery isn't why Venus is so hostile, but why Earth hasn't followed the same path.
As planets go, Earth and Venus are essentially twins. They're almost exactly the same size. They're also very close together in the solar system. In spite of that, their environments evolved in dramatically different ways.
To discover why these twin planets followed separate paths, and to explore what gave us our precious atmosphere, we have to travel back. Back 4.5 billion years to the birth of the solar system itself. The birth of the solar system created Earth's earliest atmosphere. Huge quantities of material orbiting the sun fused together into protoplanets. Jupiter and Saturn formed into gassy spheres. But on Earth, most of the material condensed into a molten core. The remaining gases bubbled forth from the liquid rock, forming the first atmosphere. Our planet's gravity stopped these gases from drifting off into space. But Earth now had to face the ravages of the solar wind, a stream of charged particles thrown out by the sun. This same wind had a catastrophic effect on Mars. It has stripped the air from the planet's surface, blasting it deep into space. The red planet's atmosphere is now only 1/100th as thick as Earth's. Our planet was spared this fate. The magnetic field generated by the Earth's core blocked the solar wind, preventing it from blasting away the fragile air. But the Earth's atmosphere was still very different from the one we breathe today. It contained high levels of carbon dioxide, a gas with a key ability to absorb and hold on to heat. Carbon dioxide still makes up 95% of Venus's atmosphere. It superheated our twin planet to the point where its water boiled away into space. And yet, this didn't happen on Earth. David Crisp believes that was down to a chance event.
if Earth kept all of its initial atmosphere, it probably would have turned out a lot more like Venus. But that didn't happen. We were the victims of a very lucky accident.
Earth's big break came 4.5 billion years ago. Back then, the solar system wasn't limited to the 8 planets it has today. Instead, a swarm of protoplanets, or planetesimals, orbited the sun like bees around a honeypot. One Mars-sized body was heading straight for Earth. In a colossal cosmic collision, it slammed into our planet, creating our moon, and according to CRISP, removing the atmosphere that still blights Venus.
Okay, the tennis ball on the string represents the early Earth during the accretion phase of the solar system, just before the moon-forming impact. And what I'm going to do now is to accrete a little bit of the atmosphere onto the top of the ball. A little later on, an object about the size of Mars passes a little bit too close by, and there's a collision which removes a large amount of the material that is accreted onto the Earth. Most of it that made up the atmosphere is just gone.
This ancient event was the defining moment for our atmosphere. With the original deadly gas mix blasted away, our planet's air could slowly evolve into what it is today.
We were left with this atmosphere made of molten rock and vaporous rock. It took millions of years for that atmosphere to fall out and to be replaced by an atmosphere made up of nitrogen and carbon dioxide and water vapor.
These new gases came from above and below. Volcanic eruptions spewed out fresh stalks of nitrogen and carbon dioxide from within the planet's molten core. While the vital element of water may have been delivered by icy comets, each impact bringing a new supply of frozen liquid. But the air still lacked one of its key ingredients.
One of the things that was missing is free oxygen, molecular oxygen, O2, the stuff we breathe.
Dr. Janet Seifert of Rice University in Texas searches for the event that produced the atmosphere's final element.
We know from the rock record that for the first half of Earth's life, there was no oxygen in the atmosphere whatsoever. There were greenhouse gases like methane and CO2, but there was no oxygen.
But the rock record shows a sudden change, dated to around 2.5 billion years ago. Evidence of the first oxygen in the atmosphere. The gas was released by a humble microscopic living organism called cyanobacteria.
Well, it turns out cyanobacteria are the only things that can actually produce oxygen. So we know that at some point cyanobacteria colonized enough of the planet in order to produce enough oxygen that it became resident in the atmosphere.
The microbes that produce the oxygen are distant ancestors of modern bacteria. Bacteria that Seifert finds living in the barren primeval landscape of Cuatro Ciénegas, northern Mexico. Over 3 billion years ago, they experienced a sudden genetic shift.
They discovered something that no other group of organisms on the planet has ever discovered. They've learned how to do oxygenic photosynthesis. They take sunlight and CO2 and use the energy of the sunlight to split water and make oxygen. And that's so important for us today because oxygen is what we breathe in. It's what made a difference to our planet that's not like any other planet in our solar system.
As the microbes multiplied and spread, the gas built up in the air, transforming the planet in a process known as the Great Oxidation Event.
Oxygen is very powerful. The world gets turned upside down. Everything has to begin to adapt to now a completely new atmosphere where oxygen is dominating.
First, the oxygen reacted with the oceans, causing iron within them to form rusty deposits on the seafloor. Then its effects reached dry land. It reacted with soil and rock, giving them a reddish, rusty tinge. And once these minerals had absorbed their fill of oxygen, the gas began to gather in the atmosphere, with dramatic consequences for life.
Complex animals could have much higher metabolisms because of the sheer potential that oxygen provided for them, and a whole different kind of evolution was able to take place.
Powered by oxygen, life evolved from single-celled organisms to complex animals. And plants also began releasing oxygen, thanks to an ancient adoption of photosynthesis.
A very ancestral, primitive plant cell either engulfed or tried to digest or surrounded a cyanobacterium. And instead of digesting it, it actually became an organ within the plant. So every bit of the oxygen, even if it's coming from a plant that you see in your yard, is coming from an ancestor of the cyanobacteria resident inside the plant.
With the rise of oxygen, the air's unique blend of gases was complete. It joined the nitrogen that plants need to grow, the methane we burn, the argon that lights up Las Vegas, and the carbon dioxide we use to fight flames. This air we breathe has changed planet Earth, molding its terrain and habitats. And as we continue our upward journey, we run into another vital substance, water.
Okay. The first thing that always sticks in my mind every time I watch that is the statement, "We were elated because we accomplished what we set out to do." I want to stick in that portion of the video for the time being and look at the structure vertically as we go through the atmosphere. Now later on we saw in the movie a little bit about moving through time. We will get there, but right now we're going to look at our atmosphere. We're going to look at our atmosphere from a vertical perspective. And so what I have here is I have two example atmospheres. I've got an example of an atmosphere here and here, and it doesn't really look like an atmosphere because our atmosphere is full of air, and this is full of water, but the water is representing the air, and it actually does a really good job of representing the air because just like air, water is a fluid, and so they both will behave in similar fashions. What I've got set up is I've got set up two 2,000 milliliter graduated cylinders, and I put 2,000 milliliters in them, and I've done my best to make sure that everything about these two setups is the same except for the position of the light. So on one we've got the light above, and on one we've got the light below. And I put these here yesterday so that way that water that was in there would have time to settle down. So you know any movement that's happening within the graduated cylinder is happening because of the light source, not because I swirled it before we started here. And so to get a look at how our atmosphere behaves, I'm going to take a couple drops of red food coloring, and I'm going to put it in both of these, and I want you to watch how the food coloring moves through the atmosphere. So when we're looking at the food coloring, just think about that as a representation of a specific place in the atmosphere, and you can track how that moves. So I'm going to go ahead and I'm going to put 2 drops in here. Oh, that light's hot. And I'm going to put 2 drops in here. Now let's watch. Okay, I can immediately see that these two are not behaving the same way. The one with the light on the bottom is mixing quite rapidly, and the one with the light on the top isn't really mixing at all. So if we look we're, I don't know, maybe 30 seconds into this trial, and we've almost completely homogenized this setup. And again, our setup over here is not moving. And that's funny for us. Which one of these represents how our atmosphere behaves? In our atmosphere, does our heat source come from above the Earth, or does our heat source come from below the surface? Does the atmosphere on our Earth turn over and mix, or does the atmosphere on our Earth stay stagnant? So, what I want you to do is be ready to have this discussion with us when we come to class. So, in your notebook, I want you to draw and describe what happened in the demonstration with the light bulb underneath the graduated cylinder, and then I also want you to describe what happened with the light bulb above the graduated cylinder. Okay. I want you to jot down a couple of your ideas about what was the difference between these two demonstrations, and then write down a couple ideas of how these principles here, how these could impact our atmosphere. All right? And then a little bit later on, you're going to have enough information in order to do the last one. So just jot those ideas down. We are going to share them out with our groups, and we're going to discuss them in class. So, right. I'm going to go ahead and turn this off. Still hasn't mixed. And we are going to move on. So, let's look at our atmospheric layers. How the Earth is heated has implications for the structure of the atmosphere. If we heat the Earth from above or from below, we will have a different result in our atmosphere, which you saw in the demo. In our atmosphere, other than the lowest layer, which we're going to call the troposphere, the other layers do not mix. The troposphere turns over. The troposphere mixes just like the demonstration with the light bulb below the graduated cylinder. The stratosphere does not mix. And the stratosphere behaves much more like our demonstration with the light bulb above the graduated cylinder. Now, the troposphere and stratosphere are separated by a barrier that we call the tropopause. And the tropopause is not a defined location. It's just where we see the difference between what's being mixed in the troposphere and what is being stagnant in the stratosphere. And so how high up it is varies based on where on the planet you are. If you are at the poles, it's only 9 kilometers up, whereas at the equator, it's 17 kilometers up. There is very little mixing across this barrier. So if we have a gas in the troposphere, it is unlikely that that particle of gas will end up in the stratosphere. The stratosphere happens to contain the ozone layer. Now, I'm pointing this out because the ozone layer is incredibly important to our daily lives, but also because this is a good opportunity to tell you that these different layers, the troposphere, stratosphere, mesosphere, thermosphere, exosphere, are divided up by airflow and not by composition. So the ozone layer, which we're defining as something by composition, is not one of these main layers in our atmosphere. It's just a component of the stratosphere. Okay. So, I want to talk to you guys about the ozone layer and the ozone in particular because of its great impact on our lives. And so, I think a lot of you know that the ozone and the ozone layer protects us from ultraviolet light. Now, most of the ozone layer isn't ozone, but there's enough particles in there to form a barrier to that UV. And so, what I want you guys to do is I want you to come and open up this simulation from PhET and go ahead and play around with looking at what happens in the ozone layer. So let's see. I want to select looking at ozone. Whoa, that was loud. And the first thing I see when I look at ozone is that it's O3, and we think of oxygen as being O2. That's the stuff that we that we breathe, that we can do respiration with, but ozone has an additional oxygen atom on it. And then we're going to take a look at what happens when you hit it with ultraviolet light. Let's go ahead and let's turn on our light source. Whoa. Let's put the molecule back. Whoa. That's weird. That's weird. So we notice when that photon of ultraviolet light comes in and it smacks the ozone molecule breaks apart, but the energy from that photon of ultraviolet light is no longer available traveling down towards the surface of the Earth where it can burn your skin and cause skin cancer. That energy is now imparted into the particles that it collided with. So we have to think about that a little bit because it'd be very easy to say, well, it wouldn't take very long before enough ultraviolet rays had come in and broken all of the ozones apart. That's true, except for the fact that you know from chemistry that oxygen does not like being by itself. It's not stable. So if you have just a single atom of oxygen, remember it has, it's missing 2 valence electrons. It's unstable, and it's going to react with the first thing that it encounters that will accept it. And so very shortly thereafter, that single oxygen atom will encounter another O2 molecule, and it will reform an ozone molecule, and it will give off the energy again that came in from the UV, but it will give it off at a lower wavelength and in a random direction, so therefore it will not come down to the surface of the Earth and cause us problems. So, yes, every time an ultraviolet photon hits an ozone molecule, the ozone molecule gets destroyed. It does reform very quickly because a single oxygen atom is unstable. So, you guys just saw how ozone can protect us from ultraviolet light, and that's really important. Now, we hear a lot about ozone because the ozone layer was becoming depleted. The amount of ozone in the stratosphere was decreasing significantly, and it created a problem because more ultraviolet light was reaching the surface. And this was a worldwide environmental problem. And fortunately for us, we solved it. And we solved it by addressing it with the Montreal Protocol, and we, as people of the world, have stayed vigilant in our work to keep the ozone layer present by banning the use of these compounds called chlorofluorocarbons. So, what happens? Chlorofluorocarbons enter the stratosphere, and when they get hit by a photon of ultraviolet light, one of the chlorines from the chlorofluorocarbon gets broken off. The problem is you guys also know that like oxygen, chlorines do not like traveling around just as an individual molecule or an individual atom. And so when that chlorine hits an ozone, it splits the ozone into an oxygen, just like when UV did, but instead of that oxygen going off by itself where it can reform, it binds with the chlorine to form ClO. Now, the oxygen is going to have a higher affinity for bonding with another oxygen than with the chlorine. And so if that ClO encounters a lone oxygen atom from another broken up ozone molecule, those 2 oxygen atoms will bond and the chlorine will go off on its own. Here's the problem. This chlorine can attack another ozone. And it can go on and on and on. We call this catalyst, right? This chlorine is catalyzing or speeding up the reaction. It's breaking it down. Now, this chlorine can be used over and over and over again and never gets used up. So it only takes a very small amount of chlorofluorocarbon in the atmosphere to wreak havoc on our ozone. Let's take a look at the ozone hole and how it's changed over time in response to the Montreal Protocol.
Every day, as the sun shines on the earth, it sends ultraviolet rays that can cause sunburn and sometimes damage our DNA. Like a sunscreen for our planet, the ozone layer absorbs most of this harmful radiation and protects us. But in the early 1980s, scientists discovered that the ozone layer was thinning over Antarctica each August and September. In 1987, nations around the world came together to fix the problem through the Montreal Protocol. The international treaty banned the production of ozone-depleting chemicals like chlorofluorocarbons, or CFCs. But these chemicals had been in use for decades, and they stayed in the atmosphere for a long time. So it took a while to see the effects of the ban. In 2000, the ozone hole was the largest ever observed by scientists. But conditions slowly improved. Data from NASA and several partners show a 20% decrease in ozone depletion during August and September from 2005 to 2016. In 2017, the hole was the smallest since 1988. A year later, the hole was smaller than expected. Studies suggest that the ozone layer over Antarctica should mostly recover by the middle of the 21st century.
Okay, so I show you that for a couple of reasons. The first reason is to get the idea that the ozone hole is not actually a hole. It's just an area with reduced ozone. And so there's not like a gaping, empty place you can travel through that section of the atmosphere. No, there's just less ozone there. And the other reason I tell you this is because this is an example of the world getting together and seeing a major environmental problem, taking action, and then seeing results. And so because of what we have done, we see that this is becoming less and less of a problem, and if we keep it up, we should be able to repair that damage. We covered a lot today. We learned about the structure of our atmosphere, and we saw that some parts of the atmosphere mix, like the troposphere. Some parts of the atmosphere don't, like the stratosphere. We also learned about how ozone is able to block certain wavelengths of light, and we focused in on ultraviolet. Now, we have a little bit of information about how our atmosphere is structured. I want you to be ready to share out in those discussions. And next time we're together, we're going to be doing a little paper and water lab, and you should be able to find information on how to prepare for that on your Google Classroom page. Thank you so much for coming to day 2. There was a ton of information that we learned today about the structure of our atmosphere, but all of it's going to play a role in understanding how we manage to change the climate. So stick with it, come to class, and we'll talk about any questions you have.